So we are in the 11th week and we are going to discuss about this bio-inspired micro robots. So as we all know, these bio-inspiring based structures or bio-inspiring based system has its own fascination. Second important aspect with respect to this bio-inspiration perspective point of view, it's a kind of a proved concept. So already it is a well established, it's a nature adapted proved concept, and it has its own advantages with reference to a particular locomotion or particular system development or system functionality, etc. So with reference to that, so it would be better that if we can understand the overall behavior of it, and based on that we go for a biomimicking capability, so that we try to take up some of the key aspects involved in this bio-inspired design, and then we try to implement it appropriately in a engineering domain, so that we can use it for different application. Like you might have heard about this sunflower tracking a sun. So this is considered to be one of the bio-inspired concept, so which is being catered by different solar panels, where they also follow the similar concept of tracking the sun. So like that. So from the bio-inspiring perspective point of view, so let us look into the micro-robotic domain. So with reference to micro-robotics, so we can take up different micro-actuations and different micro-sensing elements from this bio-inspiration, and then appropriately we can implement it. So this particular model highly focused towards this bio-inspired micro robot. Basically, as far as the key content of this bio-inspired micro robot basically involves a micro scale propulsion, a locomotion in a liquid. So in most of the cases we have seen, these micro robots are effectively used for drug delivery related applications. So with reference to biomedical perspective point of view, there is a need to understand these biomimicking based locomotion in the fluidic environment, which we will be discussing in this particular module. And then with reference to modeling perspective point of view, so let us discuss about the key technical aspects which are involved in this modeling of these propulsion system, so which we will be discussing in detail with reference to different domains, with reference to mechanical domain, with reference to electrical domain, with reference to fluid domain, etc. We have been discussing about UAVs. Okay, however, with reference to biomimicking perspective point of view, there are some micro robotic structure which works on the principle of micro mechanical flying insect. Okay, so those structures can also be effectively used for different applications, especially for micro aerial perspective point of view. So let us look into the mechanism of it, and let us look into the complete detail of it with reference to different functionality. Now, as far as in this particular module, we will be more focusing towards this micro scale propulsion. So as far as these micro scale propulsion is concerned, so when we try to talk about nature, so nature consists of numerous solutions to overcome challenges in designing artificial systems. So there are various actuation mechanisms which have been implemented in micro robotics to mimic the motion of the microorganisms. So such bio-inspired design have contributed immensely to micro scale development. Among the actuation mechanism, magnetic actuation, which we had discussed in detail in the earlier modules, is widely used in bio-inspired micro robotic system. Especially with reference to propulsion perspective point of view, such kind of micro magnetic based system has a smooth propulsion, which is considered to be one of the key advantages, and which is also has a flexibility to use it for different complex structures. So these micromagnetic related propulsion mechanism used by micro robots, which can be navigated using an appropriate magnetic field, can also be analyzed. In addition to this, considering the robots are in micro scale, they can swim inside a fluidic environment with a low Reynolds number. So in relation to micro robots, mimicking a kind of a bacteria or mimicking a kind of a fish has its own significance. Now with reference to micro robotic perspective point of view, we have the bacteria flagella, we have the sperm flagella, the cilia, and the fish are significantly considered to be a prospective candidate for analyzing the micro propulsion in a micro robotic system. So due to this fact that these biological matter consist of a different propulsion mechanism. So in this particular module, so we will be discussing in detail about the different micro propulsion mechanism which have been exhibited by such kind of micro robotic structures, and how these micro robotic structures are effectively used for a kind of a different functional application perspective point of view. So in this aspect, like we will be discussing about like how these robots are designed and developed to navigate in a complex environment such as human body for medical application or for confined spaces in the case of a microengineering task. Second, with respect to microscale propulsion in the bio-inspired robots is a crucial area, particularly for application which is targeted towards the drug delivery and the minimal invasive surgeries, and as well as in the environmental monitoring. Such kind of micro propulsion mechanisms are exhibited. These tiny robots, basically they operate in a low Reynolds number regime where the viscosity dominates over inertia, requiring a specialized propulsion mechanism which is inspired by the biological organisms. Now let us see the first case study, which is like a bacterial inspired flagellar and a ciliary propulsion mechanism. As far as these bio-inspired mechanisms are concerned, especially with reference to such kind of bacterial system, macro scale robots have mimicked the shape and locomotion of biological species. This mimicry is challenging when the size of the robot is reduced. However, due to space limitations, placing an actuator inside the robot is very challenging. These challenges has been addressed by using an untethered actuation mechanism such as magnetic actuation. So apart from that, the domination of viscous force highlights the requirement of non-reciprocal motion for a Newtonian fluid. So when we try to talk about the mimicry of the motion, the first mimicry of the motion with reference to micro robotic perspective point of view is the bacteria flagella, the sperm flagella, the cilia and fish, which has shown a promising solution to control the micro robots in the low Reynolds number flow regime. So we will be discussing about the overall motion of these living organisms, like we will be analyzing how it is actually working and how to adapt it in the micro robotic application or with reference to micro robotic perspective point of view. As far as this bacteria flagella is concerned, so this is the kind of a bacteria flagella. It is inspired by this bacteria called E. coli and other like motile bacteria that uses a rotating helical flagella for the movement. So these magnetic or electrical field are often used to drive these artificial flagella. So there are some examples like helical micro robots that rotate under an external magnetic field. So these bacteria is a kind of a living organism that can move inside a low Reynolds number fluidic environment. A helical shaped filament called flagellum is used. So this is a kind of a flagellum is used by the bacteria for the locomotion. So when we try to look into the key technical aspect of this flagellum has a capability to rotate at 100 Hz by a rotary motor connected by the cell body. So it acts as a kind of a biomimicking motor, which it's a kind of a whip. So it can rotate at 100 Hz frequency, so which will be helpful for the appropriate locomotion. See, these rotary motor and flagellum are connected through a short flexible hook which is shown over here, and it has an arrangement which is almost similar to a kind of a universal joint. In general, the diameter and the length of the helical flagellum are about 20 nanometer dia and 3 to 10 micrometer length. So these are some of the key characteristics of these flagella based system, artificial flagella based system. More insight we will discuss in detail. Now when we try to look into the overall design perspective point of view, So many computational models are developed to analyze the swimming dynamics of this artificial flagellar, because if we try to think about having a kind of a whip which is rotating at a high frequency of close to around 100 hertz, so appropriately we may need to understand the parameters which are involved, and we may need to translate those parameters appropriately for our micro robotic system. So these swimming dynamics of an artificial flagellar, which we are terming it as micro swimmers, so the model account for a fluid structure interaction between the deforming swimmer and the surrounding fluid while incorporating the applied magnetic field. Now, if we closely observe the equation behind this, the mathematical framework basically integrates the solid mechanics, the fluid mechanics, and the magnetostatics. When we look into the solid mechanics perspective point of view, the flexible polymer film undergoes deformation due to the external forces. With reference to fluid dynamics perspective point of view, the fluid drag is modeled using a Stokes-Lett based boundary element method. With reference to magnetostatic perspective point of view, the external magnetic field generates a magnetic body couples, which influence a propulsion. Now, if we closely observe the overall equation which is involved, so we have Km, the material stiffness matrix, Kg, the geometric stiffness matrix, Kd is the drag matrix. Now, del D is considered to be the kind of a displacement increments. F external is the kind of an external forces which exhibits, and F internal is a kind of an internal force which exhibits. So when we try to equate it, so we can equate it as Km plus Kg plus Kd del T equals F extension minus F external force minus F internal force. Now, when since we have already discussed about these dimensional parameters, to describe the interplay between the elastic and viscosity and magnetism, three key dimensional numbers are identified with reference to this bacterial inspired flagellar, or it's a kind of a ciliary proportion. So we will discuss about the ciliary proportion in the upcoming lectures. So it is almost similar to a bacterial inspired flagellar. Now, but it works on the principle of a magnetic field. So here we have three different systems, three different parameters which we are considering. One is a fraction of the magnetic field. Then we have the magnetic number. These are highly catering towards the propulsion perspective point of view. With reference to the type of fluid, we use the fluid number. Now, as far as in this particular magnetic perspective point of view, let us discuss about the fraction of the magnetic film. So when we try to look into the fraction of the magnetic film, we need to consider two important parameters. One is the length of the magnetic portion, and the other one is the total length of the film. So this fraction of the magnetic film is the ratio of the length of the magnetic portion and the total length of the film. When we try to look into the fluid number perspective point of view, it is represented as Fn equals 12 micro omega per G WL square by H cube. Basically, it represents the ratio of fluid drag to elastic forces, where mu is the fluid viscosity, omega is the angular frequency of the rotating field, and H is the thickness of the swimmer. Now, like this fluid level gets changed with reference to the domain what we are considering, with reference to the different field what we are considering. So in certain cases, if we are considering oil as a domain, so based on that these parameters will be exhibiting. So if we consider a kind of a biomedical fluid as a domain, then appropriately the appropriate parameters will be incorporated. Now we have a magnetic number which we term it as Mn. So as far as in this magnetic number is concerned, we have M is the permanent magnetization, B is the magnetic field strength, G is the shear modulus, H is the thickness of the swimmer, and W is the width of the swimmer. So basically it represents the ratio of magnetic to elastic forces, where M is the permanent magnetization, B is the magnetic field strength, G is the shear modulus, and with reference to thickness and swimmer perspective point of view, this is what is the relation which is followed, which basically talks about the like Mn is equal to 12 mb by g Lw by h squared L0 by L. Okay, so where we are considering the magnetic number as well as the fraction of the magnetic field. Now let us discuss about the other parameters which are being contributing towards the magnetic swimming or the kind of a magnetic actuation perspective point of view, highly focused towards bacterial inspired flagellar or a ciliary propulsion. So in this particular case, the swimming motion is chirality induced, meaning it's a kind of an helical shape which forms dynamically due to a computing magnetic torque or a fluid resistance. So almost the system looks something like this. So we have a chirality based structures, so which can take care of the overall fluid resistance with in expense of the magnetic torque. So here, if you closely observe the magnetic forces per unit volume, it is given by the relation N equals M into B. N represents the magnetic body couple acting on the structure. B is considered to be the magnetic field strength. So if you closely observe, so here in this particular case, since we are considering the chirality induced structures, here the twisting angle theta comes into picture. So in order to model this twisting angle theta, the twisting angle theta follows the from torsion theory, which is nothing but theta equals TL by Gj. T is the applied torque, G is the shear modulus, and J is the polar moment of inertia. So if we try to equate it, we can come up with this relation, which basically gives the overall twisting angle, which will be highly helpful for locomoting the structures based on our requirement. Now, so in the earlier case, we have been talking about the magnetic actuation and the chiral shape formation. Now we will discuss about the different parameters which are contributing towards the swimming velocity and the directional control. As far as the swimming velocity perspective point of view, the swimming velocity is derived using a resistive force theory, assuming a balance of a magnetic and a hydrodynamic forces. So when we try to consider the dimensionless swimming velocity, it is approximated as U analytical equals omega theta max W square by 2L CDH CDL minus 1, where since we are considering the swimming velocity, the overall fluidic domain, the properties of the overall fluidic domain needs to be appropriately incorporated. So in that aspect, we have a CDH and CDL are the drag coefficient in the width and length directions respectively. So CDH corresponds to the drag coefficient along the width and CDL corresponds to the drag coefficient along the length. So this mathematical model effectively describes how a flexible polymer based artificial swimmer can be actuated using a magnetic field. So the computational approach basically provides a key insight into optimizing the swimming velocity and controlling the directions and tuning the magnetic and the fluidic property for a real world applications. Some of the applications includes the targeted drug delivery and the micro robotic applications. Now let us discuss about some of the key outcomes of this system. So when we closely observe these bacterial inspired flagellar and ciliary propulsion, so they have a potential application especially for bio inspired micro swimmer perspective point of view. So basically it presents a kind of an artificial micro swimmer that can mimic a bacterial propulsion through a magnetically driven chirality induced motion. Now when we try to look into the computational approach, a computational model was developed to analyze the swimming dynamics, considering the interaction between the elastic, viscous and the magnetic force. Now if we closely observe the magnetically controlled motion perspective point of view, the micro swimmer movement is regulated by an external rotating magnetic field influencing their chiral shape and the swimming velocity. Now with reference to dimensionless parameter perspective point of view, when we try to look into the dimensional parameters which are identified, So the key dimensional parameters which are governing the propulsions were identified, including the magnetic viscous and the elastic contribution are considered to be the key parameters which are contributing towards the dimensionless parameters based system. Now, when we look into the other key outcomes, some of the key outcomes basically includes the viscosity induced versus magnetically induced chirality, where we have a two propulsion mechanism were compared. One is a kind of a viscosity induced chirality and a magnetically induced chirality, with the latter providing an advantages for a bidirectional motion. Now, in this particular case, so we have a kind of a bidirectional swimming which is achieved. It's a kind of a novel design which is used for two magnetic section with opposite permanent magnetization, which allows for a forward and a backward swimming by reversing the magnetic field rotation. So when we try to look into the influence of fluid dynamics perspective point of view, these microswimmer performance is strongly affected by a kind of a fluid forces with higher viscous force, leading to a kind of shape deformation, and it also has an impact on the reduced velocity. So this is where exactly, if you see, so we have the drag force which is getting contributed into flow into this picture, which appropriately have a resistance towards the overall flow. Now, when we look into the fabrication feasibility perspective point of view, the microswimmers can be manufactured using an inkjet printing and a photolithography, which are making them viable for a real world application. Now, like some of the applications basically include, like in the case of microfabrication perspective point of view, or in the case of micro manipulation perspective point of view, these kind of fabrication feasibilities are deployed. Now, when we try to look into the applications in biomedicine perspective point of view, these microswimmer holds a potential for biomedical application, which basically includes the targeted drug delivery and a micro object manipulation, basically in the kind of a lab on chip devices. Now, let us see the overall fabrication which are being deployed with reference to these micro robotic perspective point of view. So, whenever we are trying to fabricate these structures, so one of the key aspects which comes into the picture is like how these actuations are being deployed and how it is being fabricated in the form of a resin. So in fact, these are the different steps which are involved in fabricating a kind of a paramecium based micro robot, which like designed for a kind of like a ciliary based robot, and the overall fabrication which involves a kind of a laser coupled with a kind of a lithography process. So here in this particular case, like in most of these cases, either a photolithography or a rapid prototyping is deployed. So if you try to look into the features are in the range of 75 micrometers, 60 micrometers and 75 micrometers, and these are some kind of structures which are being built over here. So in order to have an appropriate actuations in certain times, so shape memory alloy structures are also being deployed. Here we could see a kind of a shape memory alloy structures which are being deployed over here, which effectively involved in appropriate contribution to the structure. So in these shape memory alloy structures, so we have a lead kind of behavior. So these lead kind of behavior gets actuated, and appropriately it can be used for the movement of it. Now, as far as in this particular structure is concerned, when we try to closely observe, so there are two important aspects which basically contributes towards the locomotion. One is called as a kind of a power stroke, and the other one is called as a recovery stroke. So in both the cases, either it's a power stroke or it's a recovery stroke, it is actuated using a kind of a locomotion. In fact, this is a kind of a ciliary based micro robot where we have a kind of a locomotion. So as far as in this locomotion is concerned, so we have two different types of locomotion which are contributed to it. One is called as a power stroke, where it is used for the movement in for the propulsion in a forward stroke, and then we have a recovery stroke where there is going to be a lift, like there is going to be a push or a recovery which will take care of the micro precise locomotion which exhibits over here. Now let us discuss about the actuation force evaluation. which are being deployed in this magnetic actuation, basically for ciliary based load. So as far as in this particular case, the cilia beating cycle generates a net translation force due to the difference in the magnetic actuation force between the power stroke and the recovery stroke. So let us consider the cilium angle theta and the magnetic force F were projected onto the xy plane to calculate the in-plane translation force in the ciliary micro robot. When an external magnetic field is applied along the long axis of the micro body at an angle with a gradually increase of 0 to 90 degrees. So like if you see in this particular case, in one particular point the cilia is bent, and in another particular case the cilia is moved in a particular stroke. So here we have the cilium angle theta and the applied field direction, which is 0 degree in the recovery stroke. Field direction is 0 degree in the recovery stroke angle, and the force generated due to the difference between the maximum cilial angle and the 0 degree. So ideally, to calculate the actuation force, we assume the cilium angle as 0 degree. After one beating cycle, the magnetic torque Tm of a cilium with an external magnetic field is described as Tm equals m into b. M is the magnetic moment and b is the magnetic field intensity. Now this has a maximum value when the magnetic field is applied orthogonally. So the equation of the magnetic force on the longitudinal axis, so we have simplified the duration as two. One is like a backward, which we call it as a power stroke, and forward we call it as a recovery stroke. So like we have the cilium length L and the field angle gamma. So the actual cilium angle, which can be represented as F equals mb sine minus theta L. So when we consider like only the planar xy plane, so the force component are counted in this calculation, and we can represent it as theta equals TL by EI, where it can be represented as mb sine minus theta L by EI, where E is considered to be the Young's modulus, I is the moment of inertia, and the applied magnetic field, like the relationship between the applied magnetic field direction is gamma, and the cilium angle is represented as theta. Okay, and the magnetic force F are calculated appropriately. Okay, so let us see a small parameters of the calculated actuation force. So if you try to tabulate it with reference to the parameters, we have the parameters, the value, okay. So the first parameter we can consider is the E, which is nothing but the Young's modulus, which is in the order of 4.0 GPa, and cilium width, it is represented as 4 micrometer, and we can nomenclate it as B. Cilium height, H, we can nomenclate it as 10 micrometer. We can nomenclate it as H, it is around 10 micrometer. And cilium length, L, which is around 75 micrometer. And magnetization perspective point of view, it is around 6,86,000 ampere per meter, and the volume V can be represented as B into H into L, and the moment of inertia I B H cube by 12, a magnetic field intensity B, which can be represented as 10 mt, and magnetic moment M, which we call it as V into M. Okay, so these are the parameters which are being considered for calculating the actuation force. Okay, so this is just to give you an overview about an equally based propulsion. What are the parameters which are involved with reference to this equally based propulsion? So we have discussed about the different key outcomes and the overall fabrication process equally and the cilia based propulsions. Okay, so next class we will discuss about the jellyfish inspired jet micropropulsion.